Okay, I think it's finally time that we start officially. Okay, hello everyone, and good evening and good morning for Dr. Henry. So if y'all are wondering whom we are interviewing today, or let's say with whom we are having this SEDS talk, yes, it's Dr. Henry. He's an astronomer at NASA headquarters, and he's managing NASA's scientific research programs and basically on outer solar system. And Throop's research focuses on outer solar system, as I already mentioned, and he's published nearly 40 articles with regards to the researches that he's doing. So today it's going to be all about New Horizons mission that he's been working on. And you also get to ask so many questions. So quickly, let's go into the session. So as my first question, I'm so curious on why Dr. Henry chose to do his PhD in planetary science.
Oh, so it's after I finished my university, I was studying physics in university, and I didn't really know what to do after that. And so I applied to several graduate programs. And the graduate programs that I ended up being most interested in and accepted by were graduate program doing planetary science, which is the solar system astronomy. And so the planets, many astronomers study stars and galaxies, which are very distant. I really like studying the planets because they're a little bit closer. You can actually go visit the planets. We can send spacecraft to go there. You can stand on the surface of a planet. So they're very physical. They're things which are very much like the Earth, but they're still in space. They're still astronomy. And so I just really like that area of astronomy, and because it's very easy to relate to as humans. So that's why I enjoy doing planetary science.
Wow, I love that. From being clueless on what to choose, he ended up being the best in whatever the field that he chose to do. That's amazing. Okay, so here we go into the main session where Dr. Henry is going to present to you the whole thing about NASA's New Horizon mission. So the question leads to, could you explain us more about the launch and the importance of NASA's New Horizon mission, which went all the way to Pluto and beyond?
Of course I will. So let me start my presentation now. The presentation will run for about 40 minutes, and then we'll take some questions afterwards. So thank you, Sarah. I'm going to start it here. I'm going to share my screen. And okay, can you see the main slide there? Nope, you can still see me, I suspect. Okay.
Yes, we can see the slide.
You can see the slide, okay, fine. Okay. Let me start off. Can you see the slide now still? I changed it.
Yes, we can see it clearly.
Okay, great. So I'm going to start off. The first question I often get asked is, what do I do as an astronaut? I'm not an astronaut. I have not been into space. Instead, I use telescopes to study the planets and the stars on the Earth. I use telescopes and spacecraft. So what do? I spend a lot of time looking at data. I use computers a lot. We use the computers to program, we do coding, analyzing data, of course, emailing with colleagues and so forth. And a lot of what we do also is writing up our results, using those to communicate with other scientists, and writing our results in scientific journals. I've been an astronomer for about 25 years. And so during this time, I've gotten the chance to use many telescopes around the world. This is one telescope that I've used in South Africa, where we're using it to look at the rotation of asteroids as they moved through the solar system. How I became an astronomer, I grew up in the United States, and I took lots of science and maths in the US. Then I got a university degree, BSc in physics, which in the US is a 4-year degree. Then I got an MSc in astronomy and a PhD in astronomy. So you add those all up, it's 4 years plus 2 years plus 3 years, that's 9 years of college, which seems like a lot, but the thing is, it was actually very fun. I enjoyed those 9 years quite a lot, especially the 5 years of postgraduate studies. And sometimes people ask about how do you afford paying for these years of postgraduate studies. In the US, most students in master's programs and PhD programs in sciences, for instance, in astronomy, biology, things like this. Most of them get a bursary and a salary from the government or from NASA or from the university where they're studying. So you don't need to pay for it. And this applies to students who are in the US, students who are Americans in the US, and also international students attending school in the US. So there are many possibilities if you're interested. And for the students who are the top students in your class, you should look at going to doing postgraduate studies in the US to get an MSc or a PhD because there's many opportunities for this. So let me talk a little bit about our galaxy. This is the Milky Way Galaxy. It has about 100 billion stars in it. This is a 1 with 11 zeros after it. And this is actually not our galaxy, but this is somebody else's galaxy. We're inside our galaxy, so we can't take a picture of it. But if you could take a picture of it, this is what it would look like. And our sun is just one of these stars in here. One of these 100 billion stars is our sun. If you zoom in our sun, you have the sun at the center of our solar system. Outward from the sun, you have the 4 rocky planets, Mercury, Venus, Earth, and Mars. We call these the rocky planets because they're basically made of rock. They look kind of like the Earth. You can stand on them. You can pick up chunks of them and so forth. So Mercury, Venus, Earth, and Mars. Outward of that, you have Jupiter, and then Saturn, and then Uranus, and then Neptune. And these 4 planets are different than the rocky planets because they're mostly made of gas. So we call these things the gas giant planets, or also the ice giant planets in the case of Uranus and Neptune, because these are mostly made of gas, and hydrogen and helium gas are in their outer atmosphere. And even though gravity is weak, they're big enough that gravity keeps all of the gas there. But that's not the edge of the solar system. We have Pluto, of course, and that's not the edge of the solar system either. Pluto is the first member of the Kuiper Belt, or the biggest member that we know of. The Kuiper Belt is this cloud of orbits of smaller bodies, of which there are many, 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 perhaps even millions of bodies in the Kuiper Belt out beyond Pluto. We can also refer to these things, you can kind of think of these things as being the icy planets. And so when you get further and further out, things get colder and colder. That's because you're getting further away from the sun. And things get, because they're getting further away from the sun, they get colder, and things like ice are stable. If you put any ice on the inner planets, it doesn't really stay there for very long, but if you put ice on the outer planets, it stays there for longer, and so you can see it more easily. For all the planets in the solar system, there's many planets which you can see with your naked eye. So here's a picture that I took when I lived in Bombay a couple of years ago. I should say that I'm living in Sri Lanka right now. I've been here for about a year. I'll be here for another couple of years, and I do hope that I can meet all of you in person sometime. I live in Colombo 3. I've enjoyed meeting some people in Sri Lanka, and just because of the current situation, it's very hard to get out and meet more people, but I hope that I can come and work in person with SEDS in the very near future. So when I lived in India, when I lived in Bombay, this is the view from my house, and I could see many of the parts of the solar system from here. So you can see the reflected light from the sun and moon right there, Venus, Mercury, Earth, Mars, Jupiter, and Saturn you can all see with your naked eye in the sky as well. Now, not all of these were up this one night. But all these bodies up the top there, you can see with your naked eye. You don't need a telescope, even from bright cities like Bombay. You can see without a telescope. And of course, you can see all these all from Colombo too, as long as it's not cloudy. Now, sometimes it's pretty cloudy in Colombo, especially with the monsoon season. But I have seen all these from Colombo as well. It's a little bit harder to see Uranus, Neptune, Pluto, and the asteroids. You need a telescope to see them because they're smaller and fainter. So I want to tell you a little bit about how Pluto was found. In 1874, there was a French astronomer. His name was Urbain Le Verrier. He was looking at the position of Uranus and discovered that there were some errors in the position of Uranus. It looked like Uranus was being pulled around by something else. So he was making plots of where Uranus should be, and it was supposed to be here, 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 and then it wasn't there. It was in a different place, and he said, I think that something's pulling around Uranus, and I don't know what it is. And so he calculated, and he thought, I think there's another planet that's beyond Uranus, and I think it must be right over here. And he pointed his telescope there and found it very near to where it was predicted to be. And this was the discovery of Neptune. It's one of the most remarkable discoveries in the history of the solar system, when Neptune was discovered soon after it was predicted by the motion of Uranus. Now, after this, someone was looking at the position of Neptune and said, oh, I think it's wrong. I think the position of Neptune looks like it's being affected by the gravity of something else. So we're going to look for another planet out beyond Neptune. We're going to call this planet Planet X, and we think it's going to be here. And so Percival Lowell was one of the astronomers who was engaged in this study for Planet X. And so he was using one of his telescopes to look for it. And he pointed his telescope around, he looked right here, and then he didn't see anything. He looked over here, and he didn't see anything. He looked over here, he didn't see anything. He spent a long time looking for Planet X. Then he died. He still never found it. But before he died, he handed off the search to Clyde Tombaugh. Clyde Tombaugh was a new young astronomer, and he used this telescope right here at Lowell Observatory to try to search for Planet X. And what he did, he used a little trick here. And so you can do this trick yourself. You know some of the constellations, like the constellation of Orion, for instance. Orion rises in the east, goes moves in front of those stars or against that pattern, then it's not a star, it's like a comet or an asteroid or a planet, something like that, because all those move differently than the stars. And so what he did is he took a picture one night, and then he came back and took a picture the next night, and he saw anything that moved relative to that constellation background. And so let me show you two pictures that he took. Here's one, and here's the next one. And so look really closely, going back and forth here. If you look in the middle here, well, I'll circle it. Okay, here's one, and here's the next one. So you go back and forth, back and forth, back and forth. And so this is actually the very first discovery image of Pluto. So this is when Pluto was discovered. This was in 1930 when Pluto was discovered. The first new planet found in the solar system in a long time. And so what we knew about Pluto back then was just that it was it's orbiting the sun. It was orbiting the sun really slowly. You can tell how slowly it's moving by how far it moved in the sky. This is about a week between the two pictures that I showed you. And because it's moving really slowly, we know it's a long way away. Because it's a long way away, and we knew it was really cold. People couldn't really tell how big it was. And then here's one picture and another picture they took of Pluto. And you can see it changes. It's kind of like, looks like it's got a little blob on one side, and the blob changes down to the bottom on the next picture 3 days later. And so that blob has changed. Turns out that blob is the moon of Pluto named Charon. It's not a mountain range, it's just a moon, but it's a little bit hard to see the moon because the resolution wasn't good enough for the telescope that was being used then. We have much better telescopes now. This is a picture taken from the Hubble Space Telescope of Pluto and its moon Charon, and you can see Pluto to the left and Charon at the right there. Now this is about the best picture of Pluto and Charon that we have ever taken with the Hubble Space Telescope. And if you want to see more, you can zoom in on this, but you're not going to see very much more detail because Pluto is so small and so distant and so faint that even with the biggest, most powerful space telescope, the sharpest space telescope that we have, we can't see very much of it. Now, we have used Hubble Space Telescope a couple more times to find some more moons of Pluto and Charon. There's two called Nix and Hydra, which were discovered in 2006. And astronomers in 2011 used Hubble again to discover the new moon called Kerberos. And then I was part of the group that in 2012 used Hubble Space Telescope again to discover the moon called Styx. And Styx is very small. It's about maybe 20 kilometers across. So it's about the size of Colombo, more or less. So the moon of Pluto is about the size of Colombo, or even smaller than Colombo. Now, if you put everything that we knew about Pluto from about 10, 15 years ago, everything we knew about Pluto onto a slide, you can pretty much, this is about all we knew about it. We knew its size because we can see it from the picture. We know its density. We know how long it takes to orbit the sun. We know a little bit about what it's made of. We know there's 5 bodies in there. It has a tiny bit of an atmosphere, but not much of one. But that's about all. You can't tell really very much more from even the best images from the Hubble Space Telescope. And so more exploration really requires a close-up visit. So how do you explore something in the solar system? Well, you can do that like you can build a bigger and bigger telescope. So we have one telescope on Earth, we could just build a bigger telescope. So if you build just 10 times as big, you can see 10 times as good. So that's one solution, but bigger and bigger telescopes are harder and harder to build. So there's a different way we can do this. We can just take a small telescope and we can instead fly it toward Pluto, just like this. And so NASA does this a lot to explore the solar system. What we do is we build small telescopes. And by small, I mean something like this big. This is about how big the Pluto telescope was, like that. And then we put this on a spacecraft and we fly it all the way out to Pluto. And so this is the New Horizons mission. Here's a picture of it right here. And this is a mission that was funded by NASA. It's operated by the Applied Physics Lab and the Southwest Research Institute, which are groups in the US. It cost about $700 million US. And this is pretty small, about 2 meters across, 2 meters by 2 meters by 2 meters or so. And this is a robot. It had no passengers, no people on it, and it just is a one-way journey. So it goes out past Pluto and it doesn't come back. And it sends pictures back over its radio. It doesn't orbit Pluto, it doesn't land on Pluto. What it does, it takes pictures and then it comes back to Earth. And it launched in 2006 and flew 6 billion kilometers to get to Pluto and arrived in 2015. And if you look at it, here's the different parts of the spacecraft. You've got the radio, you've got a camera, a couple of cameras, you've got a battery. And so what do you all have with you that might have a battery and a radio and a camera with it? You got your nice mobile here. So here we have an iPhone 12. It's got a camera, it's got a battery and a radio. And so if you think about it, really this spacecraft, this $700 million NASA spacecraft is basically the same as an iPhone. It has the same basic components and its job is the same, that it takes pictures and then sends them back over a radio link. And so if you look at a little more detail, these are the different instruments that we have, all of which are kind of like a camera where they record what's there and then send it back. And so starting at the top, we have the radio experiment, which is also the radio transmitter. We also do some science with it. We have the SWAP, which is a solar wind detector. We have PEPSI, which is a detector also for the solar wind and for plasma coming from the sun. At the bottom, we have LORRI, which is our long-range reconnaissance imager. So this is the high-resolution telescope, but again, it's not that big. I mean, the telescope is about like this. So like an amateur telescope in Sri Lanka might be larger than this telescope. On the bottom, we have the student dust counter. This was built by students at the University of Colorado in Boulder, Colorado, and it detects just single dust particles. It's kind of like a drum that detects dust particles as they hit the spacecraft. Then we have an infrared spectrometer and an ultraviolet spectrometer. Infrared spectrometer is really good at looking at the composition of the ground, and the UV spectrometer is really good at looking at the composition of Pluto's atmosphere. And so all these are bolted onto the side of the spacecraft as it flies through space. We came up with the idea for the mission about 1990. It took about 10 years until 2001, 11 years, until NASA decided to fly the mission. And NASA had to come up with the money from Congress to fly the mission. Then it took about 4 years to build the mission, design the mission, build it, and test it. 4 years is about the fastest that any mission has ever been built, any mission of this size at NASA. And then by 2006, we were ready to launch the mission. Oops, it stopped. There we go. Okay. Hang on. Okay, here we go. Here is the part of the spacecraft. This is one of the instruments. This is the infrared spectrometer right here. Here's some of the technicians bolting on some of the wires to the top of the spacecraft. And more of the wires on the spacecraft. There's many, many miles of cables if you include all of them inside of the spacecraft. Here's some of the technicians with their baby. I love this picture. It just looks like the doctors there. One of the things we had to do is take the spacecraft and stabilize it because the spacecraft is rotating through space as it flies, and so we want to make sure that it's going to be properly balanced in space. It takes many, many people. In fact, there's about 2,000 people who have worked on the spacecraft. Here is a small subset of them. This is about 200 people right here. And many of these are scientists. In the black shirt at the center is Dr. Alan Sturr, who's the principal investigator of the mission. You have many people who are scientists and postdocs on the mission. And then you have many people who are writers, who are software engineers, who are hardware machinists, people who are IT, who run the IT systems, people who are programmers, people who do safety, people who do communications, people who do writing, people who do education and outreach, take photographs and document. And so there's so many different jobs for so many different people on a mission like this. It's not just the scientists, but there's many, many people on the whole mission. So when we built the spacecraft, what we did is we built different parts of the spacecraft in different parts of the US. And so the first parts were built much of the spacecraft was built both in Texas and in Colorado. Some of the instruments were built in those locations. Then much of the spacecraft was built in the East Coast, in Virginia and Maryland, and then it was taken out to Florida to launch. And when we launched it from Florida, the whole spacecraft was assembled onto a launch vehicle, which is the fancy word for a rocket. And so the spacecraft is actually just in the tippy part, the kind of the nose cone of the rocket. You can see it right there. And so we put the spacecraft in the nose cone of the rocket, put the nose cone on top, and then you launch it. It's very exciting. So what happens here is that most of the launch vehicle is actually fuel. And so it takes a lot of fuel. Most of the weight is fuel. And then the spacecraft is only about less than 500 kilograms, even though the rocket itself weighs more than 500,000 kilograms. And so the spacecraft is less than 1/1000th of the weight of the entire mission there. The launch vehicle burns for about 40 minutes and then it disconnects. And then after these 40 minutes, then it's kind of like a bowling ball. You throw the bowling ball, you go down the lane, and if it's going in the right direction, then the bowling ball will get to its destination without having to steer it anymore. So the important part here is just push it in the right direction, and then turn the power off, and it will cruise to its destination. So that's what we did with New Horizons. So here we are a couple of days before launch, as the spacecraft is being rolled out to the launch pad. Here it is on the launch pad, and the launch pad is very distant. We're about 10 miles away. You can just barely see it on the launch pad there. But this is down at the Kennedy Space Center in Florida. We have signs here to not feed the alligators. Luckily, no one got eaten during the launch here, but there's many people on the beach here watching the spacecraft launch. And many people, here's where we were watching it launch. And here we go. Here it is as the spacecraft is launching into space in January of 2006. And so it's a very exciting time. It's a very emotional time. You can see the spacecraft going from the launch pad up through the clouds on its first journey towards space. This is one of the geologists on the mission. It's one of the artists on the mission. He works at the American Museum of Nature and Science in New York. And I'm just going to show you a quick video of the launch here. T-minus 1 minute and counting. Minus 55 seconds. And so what we're doing here is the rocket is in the center there. T-minus 45 seconds. And you can see the condensation coming off from the cold fuel. Those are the booster rockets on the side. The booster rockets just give it extra power. They're solid rockets as opposed to liquid rockets. And so the large tower next to the rocket, that's actually for lightning, because we don't want the whole thing to get hit by lightning just before launch. So it's pretty cloudy, but we know it's going to be safe going through the clouds because there's no lightning. 6, 5, 4, 3, 2, 1. We have ignition. So we're going through the clouds. We can still see it there a little bit. You'll see the merge again. Now, in a little bit, the solid rocket boosters are going to burn out. That's because they've already burned all their fuel, and they will actually pop off of the spacecraft. You'll see them fall back to the ocean. So the rocket is burning great here. So all the solid rocket boosters they've burned all their fuel. And now we're changing over to the liquid fuels on the liquid fuel part of the rocket. So these solid fuel runs are going to pop off here. And these will fall back to the ocean. All right. So our spacecraft is on its way to Pluto. It's really exciting, and it's going pretty fast. So we actually had a press conference a couple of shortly after the launch, where we had already gotten out to the distance of the moon. This is the fastest spacecraft which has ever launched from Earth. And so if you're driving to the moon, if you're driving in a really fast car, of course you can't really drive 250 kilometers per hour even down the expressway in Sri Lanka. But if you could, it would take you about a year to get to the moon in a fast Ferrari. The Apollo 11 spacecraft took about 4 days to get to the moon. New Horizons took 9 hours to get to the moon. So we were the fastest spacecraft that's ever gotten to that distance out there. And the reason is easy. It's just physics. We had a small spacecraft that was top of a really big rocket, and that gives us a lot of velocity. We needed to get a lot of velocity because we were trying to get out to Pluto fast, and Pluto's a long way away, so we needed to have all that speed to get out there. So we launched in 2006, and what did we do after that? Well, 2007, we flew past Jupiter, and then we just keep cruising out in the solar system. 2008, 9, 10, 11, 12, 13, 14, 15, 6 years of cruise, 9 years of cruise until we got out to Pluto. And if you sketch this out, here's a map of our solar system. So we launched in 2006, we passed Jupiter 1 year later, and then it took us 8 more years to get out to Pluto itself. And then we went out into the Kuiper Belt after Pluto. And so our first encounter was with Jupiter. Going past Jupiter was really exciting. It's about a year after launch. And this is actually the highest resolution global image of Jupiter that was ever seen at this time, when we flew past Jupiter on February 28th, 2007. And so you can see the Jupiter's great red spot there. You can see the zones, belts in Jupiter's atmosphere, and all this great stuff in Jupiter's atmosphere there. You can also see, New Horizons took images of Jupiter's rings. So right here is one of Jupiter's rings, and you can see 2 moons called Adrastea and Metis that are orbiting within that ring of Jupiter. This is one of maybe my favorite movie from the Jupiter flyby, and this is a movie of Io. Io is a very volcanic moon of Jupiter, and it has volcanoes going off. And here we caught, just in the act, the volcano going off on the surface of Io. And so you can see that plume, that fountain coming off, and all the material falling back. And so we had 9 years as we were flying out toward Pluto. Is that boring? No, because we were busy the whole time. So we were testing the instruments, calibrating the data, planning the observations, having dress rehearsals, testing again, writing software, upgrading things. We're very busy because we have only one chance to go to fly past Pluto. And we had to do it right. And if we screwed anything up, can we turn around and fly past Pluto again? Nope, no way. So we have to do it right the first time. And so we spent all those 9 years making sure that we would get it right when we flew past Pluto. My role, I was a member of the science team during the entire mission. And so I was involved in calibrating some of the instruments beforehand when we were building them on the ground. Then during cruise, I was developing a lot of software tools to plan the observations, searching for dust that would be a spacecraft hazard, and planning the observations. And then with the data, I was using that to look for new satellites, look for dust, look for rings, and things like that. So these are my involvements throughout the entire mission. One thing which is kind of cool here is that when we were selected by NASA, Pluto had just one moon. We had Pluto over here, and we had this moon Charon over here. And that's all we knew about in the Pluto system. But just about the time of launch, we used Hubble Space Telescope to discover 2 new moons, Nix and Hydra, which I showed you pictures of. And then we launched. And then After launch, we found one more moon, and then we found another moon after that. So suddenly, we're up to 5 moons orbiting Pluto, not just one. So it keeps getting to be a bigger and bigger and more interesting system with time. And all this is great, but it gives us one big problem. So here's a picture of Pluto. And now I showed you earlier that where you had Jupiter's rings and you had Jupiter's moons, Adraste and Metis, kind of orbiting at the same place. In anywhere in the solar system, if you have lots of moons, you're going to have rings as well, oftentimes. And rings are just dust. And dust, even a dust particle, which is tiny, 1 millimeter, a 1 millimeter sized dust particle, if you're in a spacecraft, you're traveling at 15,000 per hour, 30,000 kilometers per hour, then if you hit a dust particle millimeter across, that could be enough to damage some of the wiring or the other electronics or other parts of the spacecraft, so that the spacecraft does not function anymore, could end the mission. And so we wanted to, we were kind of concerned that if there's all these moons going around Pluto, well, maybe there's all this dust here as well. And so we wanted to check out the system and make sure that there's not dust there that might end our mission. And we can't actually look for a millimeter-sized dust grain. What are we going to do? Use Hubble Space Telescope and look for like 1 millimeter-sized dust grain that is billions of kilometers away? We can't do that. That's not practical. But what we could do is we could search for clouds of dust, and we could do simulations in our computers to model and see where the dust might accumulate. Like, is there one region of space, like between the moons or something like that, that all of the dust would gravitate toward? What we concluded in the end is that there was not dust that was just sitting around in space, and we could indeed fly past Pluto like we had originally designed. So we're flying. We launched in 2006. We were flying past Pluto, and at the beginning, we were just using Hubble Space Telescope because Hubble Space Telescope was it's on Earth or just above Earth, and we have a small telescope. So Hubble's images were actually better than our images at the beginning. But 9 years later, our images were suddenly starting to get better than Hubble's, because now we're close to Pluto, and if you're close, then you can take some good pictures. So the whole point is to get close. So here's actually the first color picture that we released of the system from Pluto and Charon, and you can see the two, Pluto and its moon Charon right there. And every day, as we're getting closer, we saw new stuff on the surface of Pluto. And so here's one image where you can start to see some blobs and features on the surface of Pluto. And then we made a movie here, and you can see Pluto and Charon orbiting each other right here. And then every day, next one image, next image, next image, and then they stopped. Uh-oh. So this is July 4th, 2015. We were downloading images, and then suddenly the spacecraft vanished. And so we didn't really know what was going on. So we started looking around for the spacecraft, and we listened for it on we have large antennas that we can listen to the spacecraft with. We were like, hello, hello, spacecraft, are you there? And the spacecraft wasn't responding. And eventually, a couple of hours later, we found it. It was transmitting on a backup frequency, and it was sending out basically messages that are saying, I'm confused, I'm lost. And we call this going into safe mode. So something had shut it down. We didn't really understand what. So we put out a press release, we looked into it, and tried to figure out why it had gone into safe mode. Now, luckily, head of our team for spacecraft operations is Alice Bowman right here, and she is one of the best people to operate a spacecraft anywhere. And so she and her team jumped into action to try to figure out what was going on with the spacecraft and why the spacecraft had suddenly vanished on us. What she found is that the spacecraft we sort of overtaxed its computers. We were asking it to do too much at one time. So she got in touch with the spacecraft, figured out what was causing it to go away. And then they actually had to rewrite system software to avoid the problem in the future. They tested out this new software on the ground, and then they actually reprogrammed the spacecraft computer from 6 billion kilometers away. So this is kind of like, you might do an update to the OS on your phone sometimes. And, you have to be really careful in doing that. You don't want to unplug it or turn the power off when you're updating the OS, right? Well, we had to update the OS for our spacecraft, and we had to do it when it wasn't designed to do this from 6 billion kilometers away. Luckily, the team was really good, and 2 days later, we were back on track. If we weren't back on track, then we might have lost the whole mission and not been able to fly past Pluto successfully. So now we're getting images back, and every day they're getting newer and better and bigger. And now, okay, so this is the Pluto flyby day is July 14th, 2015. So let me tell you what's going to happen on Pluto flyby day. This is when we get to the closest past Pluto. So we're taking pictures at about 3 o'clock in the morning. Then we're going to receive on Earth the highest resolution global image. Takes a couple of hours to process that image. And then about 8 o'clock in the morning, we'll have the closest approach to Pluto. So we're about 15,000 kilometers above the surface of Pluto. All day long, the spacecraft is busy all day long because it's taking pictures of Pluto all day long. And it's not trying to send those pictures back to us. So just like if you're, if you're taking 1,000 pictures with your mobile, you're not going to send all those 1,000 pictures to someone that same day because it takes you a long time to send them back, and you want to concentrate on taking some really good pictures. And so the spacecraft is programmed to take all these pictures and then later on to send them back. Now we have one time where the spacecraft takes a break from taking pictures and sends us just a quick phone home signal, just to tell us, hello, I'm alive, I've taken some pictures, now I'm going back to take some more. And so we were really tuned in to listen to that phone home signal, because that's when we wanted to hear if the spacecraft had successfully encountered Pluto or not. So here we are, this is the morning of the flyby, and we are at the hotel outside of the Applied Physics Lab in Baltimore, Maryland. This is the room with all the scientists and engineers for the mission assembled. And so this is about 6 o'clock in the morning. And here we are waiting to reveal and look at the first image coming down from Pluto. So let me show it here. Here we go, the very first global image of Pluto ever seen. And there it is. So this is an amazing picture, which many people spent dozens or more years in the making of. And what we find here is Pluto looked nothing like what many people thought it would look like. It looks unusual because it has many different kinds of features on it. If you look at the moon is kind of uniform. All the surface of the moon kind of looks the same. I mean, some places are a little bit more gray than others, but they kind of the same basic idea across the moon. But here, there's some blotches which are really black and some blotches which are really light. And then there's some areas with craters, and there's some areas with no craters. And then the stuff at the poles is different. And there's also this region over here that has like a heart on it, because Pluto loves us and we love Pluto too. So the moon has craters kind of all over it. In fact, the moon has so many craters on it that if you put another crater down, the only way you can do that is by knocking out a crater that's already there. It's what we call saturated with craters, because there's so many craters there. Pluto, on the other hand, on the right, it has, you see some craters. By a crater, what I mean is a hole which is made by an impact from an asteroid or comet hitting the surface. And so Pluto has some craters on it, but not that many. It's kind of like it's a really old planet, but it's sort of been like, why does it not have craters all over it? If the moon has craters all over it, you would think Pluto has craters all over it too, because they've been hit by the same stuff, basically. So you would think Pluto would have craters all over it, but it doesn't. That probably means that something came in recently and erased all of the craters from Pluto's surface. We don't know exactly why. It's been kind of a mystery, but maybe within the last 1,000,000 or 500,000 years, then Pluto's surface has been all covered up and redone. And so this is kind of like Pluto's an old planet. Pluto's made at the same time as all the other planets were made, about 4.5 billion years ago. We know that. But for some reason, Pluto's surface is much younger. So here's the science team. And these are the geologists on the team. And they're looking and seeing what, this is their reaction as they're seeing this first image from the surface of Pluto. And here it is. And I just love this because the mission team, like they're geologists and they're looking at the surface here and they're just running their fingers over it and saying, here's a valley here and here's an impact crater over here, and what caused this here and what caused this, what does this look like, and so forth. It's just amazing to see this. So we spent the morning looking at this new image of Pluto, really great, and then a couple of hours later, we were waiting till the evening when Pluto would report back to us that it had successfully been observed by our spacecraft. And so we're waiting anxiously. Look at particularly the guy in the middle on the bottom there. So we're in a room, we're waiting to hear from our spacecraft, and we're watching them. They're on the phone. They're trying to get signals from the spacecraft. And finally, we hear the spacecraft has successfully returned home, returned its data, and of course the whole room erupts here as we're hearing that. And this is super duper exciting. In fact, astonishingly, it took us 9.5 years to get there, and 6 billion kilometers. We arrived 1 minute early. So we know where Pluto is, we know which direction we were going, and you know that stuff, then get out to Pluto pretty well. So if you take this image and you kind of sharpen or saturate the colors in Photoshop a little bit, you can see different regions. We're exaggerating the colors here. And the white stuff, like, it's the pure nitrogen ice. Different colors are made of different kinds of ices. White is made of nitrogen. The red is different kinds of organic molecules, which are a little bit darker. Yellow ice, bluish ice, greenish ice signifies the water or the methane or the ethane, things like that on the surface of Pluto. So the different compositions and different history and different chemistry in different areas. Here is a region where we're looking in close up on some of the ice that's on the surface. And nitrogen ice, you know how in a glacier in the Himalaya, the glaciers, think of ice as being a solid, but really when you have gravity in there, then the glaciers can kind of flow, they can kind of slowly move downhill. And the ice on Pluto is kind of the same way. It's on nitrogen ice, but it can kind of flow, creep across the surface as well. Even though it's a solid, it's not really a solid. It doesn't really. And so we see these lines, and it looks like what's happening here is you have, it's kind of like cooking a pudding on the stove, where you cook pudding or cook some chai on the stove and it kind of rolls over and it boils. Well, it looks like Pluto looks kind of that the surface here is moving slowly and turning over, kind of like cooking some pudding on the stove. And that's because there's probably some heat inside Pluto, just like there's heat inside your stove, which is trying to get out for the pudding. There's some heat inside Pluto, which is trying to get out, and that's causing this convection here as well. We found other exciting things on Pluto, like here we have some ice mountains on the surface of Pluto, and you can see, this is in the center, you can see how big that mountain is. You can see its shadow, and you can measure it, and it's about 4 kilometers high. And so this is a shadow, a mountain, which is 4 kilometers high, which is half the size of Mount Everest, even though this is the smallest planet in the solar system. So how do you get a planet, a mountain which is that tall on the smallest planet in the solar system? That's astonishing. This big hole below it as well. Then we see steep mountains, more mountains of water ice, which are poking up through the nitrogen ice. And there's a couple of impact craters, but not that many. So it's mostly a pretty fresh and smooth surface. You can see how smooth much of this is. Now, next to Pluto, we also flew past Charon. Charon is the moon of Pluto, and it looks pretty different than Pluto. In fact, it has a lot of impact craters, not as many as the moon, but it still has a lot more impact craters than Pluto did. And it has this cracked surface in the middle, and it has this red polar cap on top. If you look at this cracked surface, that's maybe the most interesting feature of it. And it looks like maybe what's happening there is kind of like a loaf of bread. Sometimes you make a loaf of bread, and you put it in the oven, it sort of expands when you cook it, or sometimes it contracts, like concrete will contract when you cool it, and or when it cures, and you get these thermal expansion cracks. That's probably what's happening here with Pluto. That it cracked because of the thermal history and thermal evolution of the planet. With Pluto, we have these 5 moons: Styx, Nix, Keros, and Hydra are the 4 small moons, in addition to Charon, the biggest moon. We looked at the rotation of these moons, their shapes, their sizes, their histories, and so forth. We're making new maps of Pluto using suggestions for the place names from people in mythologies and explorers all around the world. So some of these things are named after astronomers and explorers from Europe and from Africa and from Asia and from Japan, from all around the world. We've named these different features. Some of the features, for instance, are named after Tenzing Norgay, who's the mountaineer who went first with Edmund Hillary to the top of Mount Everest in the Himalaya. And so these are the largest mountains. We've named them after the Nepali explorer Tenzing Norgay. I love this image here because you can see all the layers in the atmosphere there, all these layers of the atmosphere above Pluto. Even on the very, very thin atmosphere, it's 100,000 times less thin or less thick of an atmosphere than on the Earth. But you can see all these layers on it and all this texture on the surface. One more image of Pluto. This is going to scroll down, but you can see kind of the mountains on the horizon there. And as we scroll down, you can see the craters. The craters show there's sometimes kind of black and white stuff inside the craters. You can see these scratches going off on the surface. What happened to these scratches? We have no idea what caused these scratches. And you have these kind of jumbled terrain where it looks like it's frozen, and then now we're back in the mountains, and then suddenly the mountains stop, and we get to the plains of nitrogen. Everything is smooth now, but it's not totally smooth. It has bumps on it. These bumps are probably melted by the sun a little bit, but we don't know exactly what causes them. And then with these lines on, this is the nitrogen ice lines, and then in the middle of the lines, you have some rocks there, big rocks. So there's still so much mysteries in terms of what the geology and the physics of what's going on Pluto. And my predictions before we went out to Pluto is that Pluto would be small. It's small, it's cold, it's far from the sun, so it's going to be pretty boring. That's what I thought. It'd be pretty boring. There wouldn't really be much action going on. But what we found is that there's a ton going on. My predictions were totally wrong. Pluto's surface is very young. I thought it would be boring, look like the moon, but all of my guesses were completely wrong. And what it turned out is to be a much younger surface, much more active, much more geology than we really thought possible in the outer solar system. So it took us a couple of years to transmit the data because we had so much data. Just like if you take thousands of pictures on your mobile, it might take you, if you have a really slow connection, like one bar, it might take you years to send all those images back to your friends, right? And so we sent all the data back, and then we're like, well, we have a great spacecraft. What else can we do with it? So we found something else in the Kuiper Belt. And so I'm going to show you a couple more pictures of what we found after this in the Kuiper Belt, and then we'll wrap up and take some questions. So this is our map of the Kuiper Belt. We passed Pluto. We are flying through the Kuiper Belt. We didn't know where to fly, but we used a bunch of telescopes to look. Eventually, we looked with the Hubble Space Telescope to look, because the Hubble is the most powerful space telescope that we could find. That's out there. And so we found this object called Arrokoth, and you can see it circled in the circles there, where it went like one day, the next day, the next day, the next day, the next day. And if it's moving like that, then we know it's a Kuiper Belt object, which is kind of like Pluto, but a little bit further, a little bit smaller, a little bit moving more slowly, but the same basic idea. It's a small icy body, but much smaller. And so we discovered this just before we actually got to Pluto, and then afterwards we planned out how to go past it. So we targeted the spacecraft, we turned toward it, and we planned to go past it on January 1st, 2019. Now, Arrokoth is really small, and so we didn't know its size or shape or its position or kind of anything about it, and it makes it really hard to fly past it, because you don't know even the basics of how to fly past it, because we wanted to get close enough that we could take pictures of it, not hit it, and we need to know how bright it was so we can set through the settings properly on our cameras and so forth. But we're doing this in the dark while flying the spacecraft at 50,000 kilometers per hour, and it's really hard to do this. How do we even measure the size and measure the position of Arrokoth? Turns out, you would think you could just take a picture of it with Hubble, but Hubble is not nearly good enough to measure the position and size and shape of Arrokoth. Because if you just take a picture, let's take one of these pictures. This is a Hubble picture, right? Let's zoom in on it. Okay, you can zoom in on it. What does it show you? Well, let's zoom in on it again. I show you anything more? Let's zoom in on it again. You can zoom, but you have to zoom into so much, into 1/100th of a pixel to even see Arrokoth here and measure where it is. And so you can't do that with these Hubble data. Instead, we had to come up with a totally new way of doing this, which is to look for a shadow. What we did is a stellar occultation. And so we were actually waited for Arrokoth to go in front of a star, and then we saw the shadow of that star as it was going across the surface of the Earth. This is a funny observation, and this is an observation that we couldn't do with Hubble Space Telescope, but we could do with something very low tech and very simple, and that was a lot of small telescopes that we could use on the ground. And so by small telescopes, we mean telescopes which you can fit in the back of a truck. This is a picture of some of the small telescopes that we use. So we actually bought about 20 of these telescopes. These are Dobsonian 16-inch telescopes, and we bought about 20 of them. And the only way that we could measure the size of Arrokoth is by buying these telescopes and watching Arrokoth make a shadow as it was going across, going in front of a distant star, and observe it with these small telescopes. And so this is just like watching a solar eclipse. It's a solar eclipse of a Kuiper Belt object. And so we did this in 2017. We observed it from South Africa, and then the shadow path went across South America as well. So we had observers, like some of us were in South Africa, some of us were in Argentina. I was in South Africa. And here's where I was set up in South Africa, as we were on a farm to observe this from South Africa. Then we tried this again from a bunch of telescopes in Colombia. We had another observation in Colombia where we tried to observe this. So we hit it a couple of times so to be sure to observe it. So here we are in Colombia. We also used this Boeing 747 that NASA has to watch the ocean there. We did it a couple of times from Argentina, Senegal, and so forth. And so eventually we saw it enough times that we could make just from its shadow, just how, you know, if you put your hand in front of a light, you can get your hand sometimes by moving the ring. We got the shape of Arrokoth just from the shadows of it passing in front of distant stars. And so you can see in that's that kind of that figure 8 shape thing in the center here. And that was our guess of the shape of Arrokoth. So we targeted our spacecraft there. We set the spacecraft to go past it. And this was going to go past it on January 1st, 2019. So here it is. Here's a picture as we're getting closer, 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 closer. Here's our control center outside of Washington, D.C. in Maryland. And looks like we're on target to see it. But, you know, even just one day before, this Arrokoth is so small, even one day before we got there, this is the best image that we had of it. Our targeted flyby was supposed to happen on New Year's Eve. And so most people were celebrating New Year's Eve at midnight. Well, we didn't celebrate at midnight. We celebrated at 12:33 a.m., 33 minutes later. And that's because that's when the spacecraft actually flew past Arrokoth. This is Alan Stern, the principal investigator, along with Alice Bowman, who's the head of mission operations. We successfully flew past Arrokoth. And here's our very first picture of Arrokoth that we took. We did a pretty good job of predicting the shape of Arrokoth. What we measured from just using a bunch of cheap telescopes in the back of pickup trucks was pretty similar to what we saw from the spacecraft itself. It was really remarkable that we could predict its shape and size and position so well. So this is part of the team that predicted that. Really excited for this. And as the data came down, we started to get a better and better picture of what Arrokoth looked like. And you can see on the right, that's our best picture on the far right of what Arrokoth looks like. And what you can see kind of looks like a snowman. You know, it has like a blob here and a blob here, and has some craters on it, but it's very small. This is about the size of Colombo. It's about 10 or 20 kilometers across. This is the oldest thing that we have ever seen in the solar system. This is a rock. This is a giant rock which has been untouched for 4.5 billion years. So this is what the planets are made of. There's no argument whether this is a planet or not. This is not a planet, but this is what the planets were made of. All the planets were made of stuff like this. And this is a region of the solar system that we've never visited, and it has never visited us. So this is the most ancient thing in the solar system we've seen, and it's so exciting to see it. We don't know why there's 2 different bodies here. Maybe it used to be 2 different bodies and they came together. You can see some craters here, but not very many. You can see both objects here have the same color. They're both red. The bottom kind of looks a little bit lumpy. Maybe like this other lumps that kind of all came together, kind of like this. Other lumps came together to make Arrokoth like this. We don't know exactly. But then what probably happened is you had 1 million of these things, and they all kind of came together to make Pluto. Like that. So there's still many, many questions that we don't know about this. Is this like other Kuiper Belt objects? What's the geology going on? All of our data, we actually are still, that should say September 2022. We're still downlinking some of the data because not all of it is downlinked yet. Arrokoth looks kind of like some other things in the solar system where we have, bodies which are very young and very pristine and stuck together. And New Horizons continues to go through the solar system. The spacecraft is still flying through the solar system. In another 8 years or so, it's going to get to the outer edge of the Kuiper Belt. We're going to search for another flyby target. We haven't found one yet, so we don't know whether we find one yet or not, find one or not. But New Horizons is doing some other observations if we don't find another flyby target. In about 50,000 years, it's going to leave the solar system. In about 500,000 years, it'll fly by a distant star. Of course, by that point, the batteries and fuel will be finished up. So maybe in 2040 or so, then the spacecraft will stop operations. But we hope to keep it going as long as we can. So thank you so much from the team. Here's many of the people who are involved in flying the spacecraft, and I hope that you will tune in and continue to follow the mission here. Here's the web for the mission. And of course, I would be happy to take questions that you have. Thank you so much.
Thank you so much, Dr. Henry. We loved the presentation, and I think everyone here got lots of information. And I believe that there are so many questions at that part. I would like to ask some questions, which I already had in my list. And the first one is, astronomy is a broad sector with so many branches to it. Well, even though people from developed countries have a handful of experiential concepts, people here in Sri Lanka, we lack opportunities to get these practical ideas because we don't get to see a launch, and we don't get to do so many other things that people who have a space agency in their own country get to do. So what are the initiatives that could be done to improve this field in Sri Lanka?
I think there's much that Sri Lanka can do. Even though Sri Lanka doesn't have a space program that's launching rockets and spacecraft, there are many things that people can do in Sri Lanka. First of all, there are it's easier and easier to put small things like CubeSats and like weather balloons that have instrumentation on them, and things like this can be, for very low cost. You can take a balloon and fly it up to space, make measurements this way from Sri Lanka, and so you can do unique observations here. With occultations, these can be measured using small telescopes, telescopes which cost, which have a aperture just this big or so, just the kind of the size of a camera, and you can do very important observations of asteroids from Sri Lanka. And then there's many opportunities for students in Sri Lanka who want to attend university or do postgraduate studies abroad, become involved with the work that is done in India or in Europe or in Australia or in the US or other countries.
Okay, I think that answered my question. So even to pursue higher education, we might have to emigrate, so that that will pave the way in case if we want to do things like aerospace engineering, astrobiology, astrophysics, because we don't have those things here in Sri Lankan universities for bachelors. As my last question, as developing nations, developing space sector has a very less possibility considering the misunderstanding and lack of knowledge about its importance, especially among the older generation. So as a researcher who has more experience with contributing to the development of space sector in developing nations, what are your suggestions that could help clear the wrong ideologies and pave a path for youngsters to follow their dreams in space science?
Well, I think the most important thing is just education and talking with people. So I think all of you, if you're interested, what I like doing is exploring the world. We have so many questions about how the world came and how the universe was created and how we ended up here. And I think astronomy is so interesting to people because you can answer these questions. You can answer these very, very basic questions of how the universe got here and how it evolved. And I encourage all of you to, keep asking questions and keep studying the universe around you. And by doing this, you sort of, you explore this yourself. You bring other people along for the journey as well, and this kind of helps to create this culture of asking questions, of learning, and growing, and of developing, even in a country like Sri Lanka that doesn't yet have its own space program. So I think that by doing that and by encouraging everybody to be curious, ask questions, then you really start to expand that in the country.
That's a great suggestion. So now we go to the part where the audience have asked so many questions. The first one is, Dr. Throop, any specific tools, software, or platform suggestions to get started with the research and education into the Kuiper Belt and beyond, and any open sources that you could recommend, just like Astrometrica, WWT, etc.
Yeah. Certainly, I have. There are so many different tools that are available now. It's most of the tools that I use, for instance, are freely available. I do a lot of coding in Python. I use NumPy, and there's a library called AstroPy. There's a plotting library called Matplotlib. There's a dynamics package which shows you the position of everything in the solar system. It's called SPICE. It's by NASA's Jet Propulsion Laboratory. And so all of these libraries and things like that are kind of freely available for everybody to use. Moreover, all of the data from all of NASA's spacecraft are available freely for anybody around the universe to download. And so anybody in any country can download them, whether you're on Earth, or I guess someone on another planet could download them as well. And so all of the data from New Horizons, anybody can access, whether you're in the US or whether you're in Sri Lanka. You can go to NASA's websites and download all of the New Horizons data. And so it's very, it takes a long time to analyze these things because they're complicated. It requires a lot of deep focus to understand the data and to analyze them properly. But there are a lot of people out there to help, and there are a lot of, given sufficient time to analyze the data, then you too can contribute to the knowledge generated from NASA's missions.
Thank you. The next question is, just thinking out loud, could the well-preserved craters, like the Sputnik Planum, be a result of Pluto and Charon being mutually tidal locked as binary planets, and potentially the ice glaciers preserving?
So yeah, that's a great question. We don't think that Sputnik Planum is the result of just a tidal locking. So you can calculate how much, Pluto and Charon are kind of rotating like this, where they're each seeing the same side all the time. And that's true, they're tidally locked, but the force from that isn't enough to actually cause the depression from Sputnik Planum. Sputnik Planum, which is that heart-shaped thing on the surface of Pluto, is probably caused by an impact crater into it. That's that's kind of what the thinking is. Not guaranteed to be right, but that's what many people think.
All right. The next question is, I'm an engineering student and I'm fascinated about MATLAB. So my question is, have you had experience with MATLAB in your work? And if so, how important is MATLAB?
Okay, yeah, MATLAB is great. I haven't used MATLAB myself a lot. I used something called IDL, which was at one point kind of a competitor to MATLAB. But IDL went in one direction and MATLAB went in another direction. But MATLAB is certainly used by a lot of science and engineering students and professionals widely. It is probably, now there are probably more people who are using Python than MATLAB, at least in science research. Maybe not in engineering, but in science, there's more people using Python. And that's just because Python is available for free. Anybody can add to it. Anybody can download the libraries for free. There's lots of free support, like through Stack Exchange and so forth. And so for me, doing the work that I do, Python is really is just such a great environment.
All right. The last question, I think, that is, what are the telescope specifications suggested for KV observations? Is a 16-inch Newtonian good enough? Open source or CRDS components that can be used for this purpose? Prospects of an observatory.
Yeah, okay. So if you're actually trying to detect Kuiper Belt objects, a 10-inch telescope is not usually enough, because to actually detect a Kuiper Belt object, most of these are done with very, very large telescopes, which are, have mirrors that might be 3 or 4 or 5 meters across. So some of the largest telescopes on Earth, really, or up to 10 or 12 meters even. And so, however, there are some occultations of stars by Kuiper Belt objects and by asteroids, which you can detect with a 10-inch telescope. I myself, I don't even have a 10-inch telescope. I have an 8-inch telescope, and I've detected occultations of not Kuiper Belt objects, but of asteroids using this telescope, and it's pretty easy to do so. So it requires a lot of the, the hard part isn't actually doing the observation, but it's setting up and learning, how to do the observations and so forth. But what these are observations where the asteroid goes in front of a star and blocks out the light from the star. So if you make a plot of light, it's like bright, 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 and then suddenly the star disappears, goes away, and then it comes back right here. And so these observations are really useful for measuring the position and the shape and the size of an asteroid. And if you're interested in looking at these observations, then you could look at, there's a group called the IOTA, the International Occultation and Timing Association, and you can talk with them or look at their website, and you can certainly send me an email if you're interested in doing these sorts of occultations observations from Sri Lanka as well. Hello, Sarah, have you returned? I can't hear you.
Yes, hello, Mr. Henry. I'm Hassan here.
Hello.
So yes, as in Sri Lanka, we are. Sorry, so as in Sri Lanka, we are experiencing some power cut issues. So yes, Sarah is facing the difficulty of power cut.
Oh, yeah, of course. It's very difficult in Sri Lanka right now, I understand.
Yes, exactly. So we have a few more questions. I'll just go run through one of the questions. So an interesting person here is asking about the craters again. So he's just saying that he's just thinking out loud. Could the well-preserved craters that the Sputnik Plenum be a result of Pluto and Charon being mutually tidal locked as binary planets? And potentially the ice glaciers preserved?
I think we already answered that question. It's probably not tidal locking. It's probably just an impact in causing Sputnik Plenum.
Great. All right, so I guess that exhausts all the questions from the audience as well for today's evening. And I hope everybody here who just joined with us had a wonderful time listening to Mr. Henrythroop here sharing his knowledge on the New Horizons space mission. And I hope we answered most of your questions to the audience. And we welcome questions as well. We would be willing to answer any more questions. You can contact the SEDS Sri Lanka page through any of our social media pages. We have YouTube, Facebook, and many more. So stay connected with us through all the social media pages. And I would love to say it was a pleasant session, and all the thanks goes to Dr. Henry here. He spent a lot of time explaining all these things to us. It was a wonderful session, I would say. So thank you everyone for being with us together through all this session. And I hope everyone is having a pleasant evening. So have a nice day, everyone. Thank you so much, Dr. Henry.
Thank you so much. And I hope that we can meet in forward with all of SEDS at a future date. Before we go, I just want to see if there's any more questions that anyone has, either through the Pigeonhole webpage or through in person. If there's any more questions, we have a couple more minutes if anyone would like.
Yes, we'll give around 2 minutes so we can see
that's fine.
If we have more questions.
I see a couple of hands raised.
Okay, guys, with the hands raised, could you please drop your questions on the Pigeonhole, the website? It would be much more easier for us that way.
Let's see, someone asked my contact information. You can, if you just search for it online, you can find it easily enough. You can find my email address there. Let's see, someone asked for bring hands-on search for Kuiper Belt objects closer to our in Sri Lanka. There's a lot of research that you can do online. It's hard to search for Kuiper Belt objects directly in Sri Lanka, but I think being involved with these occultations is really exciting. Where you can look at, maybe I'll give a talk in the future of that, because that's something where that SEDS really could be involved with. These occultation observations can be done using small telescopes from Sri Lanka, and it would be nice to work with SEDS on a project involving those. There's one question about, it says, we at Space Lab, Dream Space Academy would love to bring that. Oh no, sorry, next one down.
Yeah.
It was about Mars rovers.
Doctor, there's a question about Rover. So basically, through
Yes.
SEDS, we are competing in the ERC challenge, that's the European Rover Challenge this year. So we are actually coming up and building our first ever rover that is made in Sri Lanka itself, designed and built in Sri Lanka.
Yes.
So any suggestions that you have in general for that, or anywhere that we can look for support? Because currently with the country situation, we are struggling to get some support, like we need a lot of mechanical parts and financial stuff as well. So what are your general suggestions then? What are your supports that you can do?
So, regarding the financial situation, it's very hard in Sri Lanka for everybody right now.
Yes, sir.
I'm here too, and I see this every day. As trying to get fuel and trying to, keep power and keep connections and so forth. So, I hope very much the situation will improve, because the country has so many great on, and I hope that the situation will improve so that all these can be utilized. For the specifics of building a rover, it's building a rover is not that hard. But the hard part is making a rover which will work for a long time and work reliably. It's very easy to build a car that has wheels that will turn, but then you have to make sure this car's wheels will turn, given years and years of operations on the surface of Mars, or on even a moon rover, or some other planet. And so long-term reliability is the most important thing. So my suggestion would be keep the mechanisms simple. Don't try to put too much onto it. Keep it simple, and get the simple things working first, rather than try to make a complex rover. Build a simple rover and make it reliable.
Okay, yes. So our focus would be on making that, as you say, and we will talk to the team as well. So first thing is to build a reliable rover, isn't it?
Yes.
So that's great. Yes. So there's one more question, I guess. So, sir, with the launch of Capstone tomorrow, we are entering a new era of space exploration. What are your opinions on it and space exploration beyond Earth and Moon?
Okay. So Capstone is the it's a cislunar autonomous positioning system technology operations, and so this is a lunar destination CubeSat. So there's a very small mission which is going to the moon. This is exciting because this is one of the first very small modern missions which is going to the moon. It's easier and easier to go to the moon, and so this sort of thing which there are some small missions which have been in orbit around the Earth, which have been built by students, and so space is becoming more and more accessible to students and to small universities and so forth, through better launch vehicles, through improved electronics, through more reliable electronics, through better software and so forth. And so this is this Capstone mission, for instance, is a great example of how even with a lower and lower budgets, then you can do significant research and build hardware which will operate in space. So I think this really kind of serves as an inspiration for so many groups.
Okay. Yes. Great. So indeed, it's a new stone, like it's a new milestone, isn't it? We are stepping into a new era.
Yeah, very much.
Yes. So I see no more questions again. Let's see, just a little more time.
Someone asks, is there any paid or free NASA courses
Yes.
or apps for kids? There are let's see, on the NASA website, there are, there's an excellent book for kind of university students about how to build and design a spacecraft. And I think it is called, written by a guy named Dave Doody. DOODY, and I think it is called Basics of Spacecraft Design or something like that. I can send out the link if you send me an email to follow up with it. It's for older students. I mean, it's for students, not for younger kids. But there are many educational activities and outreach activities for younger students as well. If there's areas of the NASA website which are with school age activities, and I encourage you to look for those. There's many of them out there. Someone asks, what can I do to get our degree in the US? Because it's so expensive right now. What I would encourage you to do is, it's very expensive to go to the US for an undergraduate degree, like for a bachelor's degree. So there are many good schools in Colombo. Get a bachelor's degree from in Sri Lanka. And then for the people who are at the top of their class in Sri Lanka, then you would be in a position to be competitive for graduate programs or postgraduate programs in the US or Europe or Australia. And many of these come with bursaries, so that even students from Sri Lanka would have much or all of their education paid for if you're accepted to these graduate schools and are at the top of your class. So there's many opportunities there. And then finally, let's do this last question. Someone asks, I'm very interested in studying about life beyond Earth. My ambition is to help the world find life beyond Earth. What are the qualifications do I need to achieve this study? And basically the qualifications is become an astronomer. And what that entails is go to graduate, is study, get an undergraduate degree, get a BSc in one of the sciences, find out what you're most interested in, go to graduate school, get a PhD. And a PhD is kind of where what most research scientists have. Get a PhD from a degree from a school in the US or Europe, Australia or India, one of these major countries. And by the time you do that, you will know what the issues are, and you will essentially be a scientist working in this field. And then you can really make contributions to the world. So I encourage you to all continue to be curious, work hard, do well in school, and continue to explore the world around you. So thank you.
Yes, thank you so much, Dr. Henry. As Dr. Henry said, yes, there's so many of ways, and the internet is free. Everything could be explored through the internet, and information could be and found through the internet as well. So use all the tools and the support that you have wisely. As students of Sri Lanka, it's our responsibility to bring up the country as well. So I hope this was a pleasure, and it's been an honor to have Dr. Henry here as well today evening. He spent his time to us. So thank you so much, Dr. Henrythroop. And we hope to work with you forward in our upcoming sessions as well. And thank you everyone for being with us here in this evening and sharing this session with us. So I hope everyone to have a pleasant day. And thank you once again. You all can, the people who requested the recording for the session, it will be uploaded on our social media page, and especially on our YouTube page. So stay connected with SEDS Sri Lanka's social media pages, and we will be bringing you much more SEDS Space Talk and some knowledgeable sessions as such. So have a great day, everyone.
Bye-bye. Thank you.